This video we're going to look at what we need to know about polymers at A level, the two different types of polymer, how to draw repeat units and equations for polymerization reactions, and a few other bits that we need to know about the different physical and chemical properties of polymers and how we can link that to our A level knowledge of structure, bonding and intermolecular forces. So, the proper definition, we really need to think that a polymer is a very long molecule. So it's not enough just to join, say, 3 amino acids together. That's a tripeptide. So we use this word macromolecule, and if anything, this is a better use of the word macromolecule than when we talk about like diamond or graphite, which isn't really a molecule. It doesn't have molecular properties. Polymers do have molecular properties, so they are held together by intermolecular forces, and we'll come to that later when we look at the physical properties of polymers. So there is many small molecules. When it comes to monomers, generally polymers, we're talking at least 100. Certainly, maybe you want to talk about like maybe having 1,000 atoms in a molecule. So it's long and it's repeating as well. So there is some sort of repeating unit, and that's going to be quite a focus of this video, is how we identify those repeating units and how we draw repeating units for some of those slightly more difficult examples that we get at A level. So there are only two ways really that we can make polymers, and that is either through addition reactions, which we should be really familiar with if we are more than a year through A level already, but we come across them at GCSE even. So addition reactions happen with alkenes. So we are looking for a C double bond C, and that is going to open up during the reaction. The carbons stay joined together and it's going to join on to other molecules. Now, one thing to be aware of is that although addition polymers are made of alkenes, we're at A level now. The context can get a little bit more difficult, and the groups that are attached, I shouldn't have chosen A, B, C, D because now I've got a C on there. They can all be different functional groups as well. Okay, so you can get an alkene with a carboxylic acid or with an alcohol on it, and that is going to affect the sort of overall properties of the polymer. The side chain groups are going to affect the intermolecular forces, but generally what's going to happen in the backbone of an addition polymer is it is just going to be carbon-carbon single bonds. That affects their chemical reactivity, and we'll have a look at that when we look at addition polymers in more detail. And then condensation reactions, we should have come across them again at GCSE, and we come across them at A level, usually towards the end of the first year, beginning of the second year. So we should know in a condensation reaction, this time we're joining molecules by loss of a small molecule. So we are not just saying the molecule is water. It doesn't have to be water. It could be HCl. There are other small molecules that could be lost. Our traditional example that we do at GCSE is carboxylic acids and alcohols, but it could be other functional groups, and we'll have a look at some examples of those. But the idea is these are not alkenes. These are things where we can take off a small group of atoms, such as an H and an OH, and make a small molecule such as water, and then join the other atoms together. So let's look at addition polymers first, because that's the ones that we cover first of all. And we are going to look at how to write a balanced equation for polymerization. So we're not going to do anything easy like ethene. We should know how to do that already. I'm going to use a more A-level example. So we're going to use butene, 4 carbons, double bond between the second and the third. Now, if we were drawing out butene, if a question just said, draw a displayed formula or a structural formula for butene, more than likely you're going to follow your rules, which is get your 4 carbons in a row because it's but. We're going to put a double bond in between the second and third carbon because it's butene, and then we can just, put our hydrogens on, making sure we carefully count so that every carbon's got 4 bonds. There we go. Now that is perfectly legitimate displayed formula for butene. I could also draw a structural formula like so. However, this is not a good start if I want to do a polymerization for an addition polymer, because I need to show the repeat unit of the polymer, which only involves the double bond. So those CH3 groups can't do anything chemically. They're not going to react. They're not going to undergo addition reactions. So in order to make sure that we don't make any mistakes, we need to get them out of the way. So we are going to redraw our monomer always in addition polymerization, and of course if we're trying to do EZ isomers as well, then we need to be drawing it with the approximate bond angles. You can stick them straight up rather than having them sort of at 120 degrees, but the real bond angle is 120. I'm then going to put in my CH3s and my H's, and for the purposes of this, it doesn't matter. So if you're aware about EZ isomers, you'll realise I've drawn the E isomer, or the trans isomer of this molecule. It doesn't actually matter in the purposes of polymerization, because polymerization is just going to happen in all random directions, and we're going to lose the double bond, which means we're going to be able to rotate those carbons around, and so it won't have any EZ isomerism in the polymer chain. So it doesn't matter which way round you draw it. Okay, and then we drew an arrow, so it's an addition reaction. I've got nothing else to add except the alkene to itself. Very easy now that I've drawn it correctly to just take out the double bond. Don't change anything else at all. And then we need a nice, it can be a stupidly long bond, especially if you've done an angle like I have, or you can fudge your square brackets so that they don't sort of go all the way around. It doesn't matter, as long as the bond comes outside the brackets. That's what they're looking for. Now you're going to ask, what about the N? What does the N do? Surely the N is really important. It's not the most important bit. What we use the N for is just to balance the equation. So N is just a number of molecules. So let's say N is, 500. 500 of those joined together to make a polymer which is 500 long. That's why we put it in a different place. So the N is like a number in front in a balanced equation. We put it in front of the molecule. And then the N there after the repeating unit is like the kind of number that we would put in a molecule such as Cl2 to show how many of them there are, but they're joined together, so the number doesn't go in front anymore. The N is going to be more important and perhaps a little bit more challenging when we look at equations for condensation, polymerization. But there's an example. So the main thing with drawing an equation for an addition polymer is to get your alkene with the correct bond angles. Okay, now we're going to look at what about if they give us some examples, repeat units and monomers. What do we need to be able to do? We need to be able to look at a monomer like butene and draw a repeat unit. Now we've just done that because we drew the repeat unit in the balanced equation. We might want to look out for questions that say things like draw two repeat units. Okay, so we have to draw two next to each other. Identifying the repeat unit from a chain and identifying the monomer, which are very similar but slightly different things. So let's have a look at this section of polymer. I chose this one specifically. This is PTFE, which is Teflon, but the reason I chose it is we need to be careful about what we mean by the word repeat unit. So you might think that the smallest possible repeating unit that I can see here is basically CF2. So there's one carbon and two fluorines, and that repeats all the way through. But when we say repeat unit of a polymer, it's an addition polymer, which means it came from an alkene. So actually, there can only be even numbers of carbons, and the repeat unit, therefore, all I need to do is take any two carbons along in the chain and put a bracket around them, and that is my repeat unit. And if I want to draw the monomer, I simply draw that exactly as it is, and I put the double bond back in. And if I want to name the monomer, that is tetra going to run out of space, fluoroethene. That is all one word. I just ran out of space for putting it in. Okay, so 2 carbons wide along the chain. Of course, there could be all sorts of different functional groups. I'm going to do the same thing again with this thing. Stretch it round, 2 carbons wide. It doesn't matter where I do it, I'm going to get the same molecule. Put the double bond back in and draw everything else exactly how it is, and that molecule would be ethenol. Whoops. Which is a bit of a weird word, ethanol. So it's basically ethanol with a double bond in the middle of it. So this is an example of a polymer that has another functional group. So does the other one. It's got a haloalkane in it. So that doesn't matter. We just draw those exactly as they are and we put the double bond back. Okay, what about if we have skeletal formula? It looks a little bit more challenging, but it's really not. Now, this isn't the nicest example of skeletal formula. I wouldn't draw CH3s on the end. That's just because the drawing package does that sometimes. But look what I'm doing. I'm basically just going to put the double bond back. There it is. So I got rid of those and put the electrons back in between the 2 carbons. I could now sit and name that. I've got to be careful about the longest chain. So I've got 1, 2, 3, 4. It doesn't matter which way I go. 5. So the main one is called pent. It's an alkene. We're going to put that double bond between the first and second because that makes more sense than the fourth and fifth, smallest numbers. So it's pent-1-ene, and then there's that one other carbon here, which is 1, 2, 3. That's on carbon number 4. So we have a 4-methyl pent-1-ene is the name of the monomer that makes that polymer. And then we could have something else, which again, it's sort of skeletal messes with people's minds. So remember that we need to identify 2 carbons. So every addition polymer, the repeat unit is 2 carbons wide. So in a skeletal formula, that is 2 carbons there. So I could put my bracket there and my bracket there. And there I have my repeat unit, and you can see that it does repeat. There's the next one along. So if I wanted to draw the monomer, it's just going to be like that. So even if you're at the start of A level and you've not seen a benzene ring, you don't really know what it is, you can still take that structure and draw your repeat unit. Okay, let's move on to condensation polymers. So remember, they are made when monomers join together by loss of a small molecule, and that small molecule could be, for example, when we lose H2O and we join them together with an O. We could lose H2O from a different group. So if we have an amine, same idea, we're going to lose the H and the OH, and then we're going to join together through the nitrogen, which is going to have a hydrogen on it because it's got an extra bond. Or we could lose HCl and then join together the atoms that had the Cl and the H attached. Let's start with our carboxylic acids and alcohols, which is our most common example of condensation that we sort of know about. So, big difference with condensation polymers compared to addition polymers is that you might need 2 different monomers. We are going to look at situations where you only have 1 monomer, but what you definitely need is 2 functional groups, because other than alkenes, functional groups don't tend to react with themselves. So an alcohol isn't going to react with another alcohol, and a carboxylic acid isn't going to react with another carboxylic acid. So you need 2 functional groups. They both need to be able to lose an atom or 2. So one of them is going to lose an H, that's always the case. The other one is going to lose an OH or a Cl. So what we have here is a dicarboxylic acid at both ends, and a diol. This is a sort of quite simple example. At A level, how they could make it more challenging is, for example, carboxylic acids don't need to be in a nice straight line separate from each other. They could be at awkward angles, and we'll have a look at some examples. But let's just get to the basics of what we do. So when these two monomers join together, we need to lose 2 water molecules. So we're going to lose both the OH groups on the carboxylic acid. If that was an acyl chloride, that would be a chlorine there instead of an OH, and we'd be losing the chlorine. And then on the diol, so that is a diol, an alcohol at both ends, we are going to be losing the 2 hydrogens. So to draw the repeat unit, and what I'm sort of doing here is drawing an equation as well, these would be my reactants. What we've got to do here is, what I've done is I've drawn everything except the OHs and the H's, and then in the middle here we've got our O joined to that carbon with an ester group in the middle. So we're making a polyester. And then to do the repeat unit, we've got to do our bonds outside the bracket. So there is no OH on this side because that's been lost from the carboxylic acid. There is no H on that side. So I should make sure that if I join those two ends up, I get an ester again. So I don't have any extra oxygens or not enough oxygens. And of course we put square brackets. Now we can put an N next to it. So if we had N of those and N of those, and we would actually make a very confusing 2N minus 1 H2Os. You can also get away quite often with just writing 2N. So the reason it's 2N minus 1, hopefully you can see why it's 2 lots of water molecules, because we've got 2 OH groups and 2 H groups to lose, but at the end of the molecules they won't be lost. So somewhere right at the end of this molecule there will be 1 less water molecule because the polymer is not infinitely long, it's got to have ends to it. However, you would probably just get away with writing 2N H2O. Okay, let's have an example of something where there's only 1 monomer, but it has 2 functional groups. This is lactic acid, otherwise known as 2-hydroxypropanoic acid. It's got carboxylic acid and an alcohol group, and we are going to show how that would form a polymer. So I can just draw it skeletally. It's good to get comfortable doing things. I'm not going to draw the shape though. I'm going to have N of them, and I'm going to have an arrow, and I'm just going to take off the OH and the H. So I'm going to keep my C double bond O. I'm going to keep my methyl group, and I'm going to keep my O. And then I've got a bond here, which is going to go to the O of the next molecule. So, bit of an awkward bracket, that's terrible. Let's do it slightly better angle, there we go. That's going to go out there, and then that is going to have a nice straight line, much easier to draw. There are going to be N lots of those, because it's only 1 monomer and it's just going to keep joining together, which means there's only going to be N H2O molecules. Weirdly, in fact, there's going to be N minus 1 H2O molecules, but let's not worry too much about the balancing. It's more about being able to draw the repeat units. And of course, like our addition polymers, we need to be able to identify repeat units or identify the monomers from the repeat unit. So here's a repeat unit of another polymer which has been slightly weirdly drawn. I wouldn't recommend drawing it like this, but they've obviously done it sort of just kind of get you thinking, or it's just a bad drawing. So this is a polyester again. I can see the C double bond O's, so actually what I want is just to separate that bit out. So I'm going to take my benzene ring, draw it exactly the same, take those bits and stick my OHs back on. Now it could well be that this polymer wasn't made with carboxylic acid groups. It could have been made with C double bond O CLs, but if you don't know, then you're going to assume it was made from carboxylic acid. Or if you're drawing what is made when the polymer is broken down, then you're going to draw the carboxylic acid. Then we've got this section. So I know I've got a CH2, a CH2, and that's going to be a diol, so I'm going to put the H back on there. The O that is here is actually over here, which is why I said it was a bit of an unusual diagram, but it all balances out that that is the correct repeat unit, just ethane 1,2 diol. So I've identified my monomers from that, and the other one is benzene dicarboxylic acid, 1,6-dicarboxylic acid, no 1,4, sorry. Okay, a couple of other examples where one of them we're going to draw the repeat unit and the other one we're going to use the repeat unit to work out the monomer. And these again are examples where there is just one monomer but with two functional groups. So what a horrible looking kind of structural skeletal formula we've got going on the left hand side. Again, it just takes a little bit of practice, and if it's a funny angle and doesn't look quite the same, as long as it's got the same number of bonds in the same order. Oops, I've drawn my OH in because I was talking. I'm going to put a benzene ring rather than those double bonds. So I'm going to take that off. I'm going to take that off. So I'm just identifying there is no OH group there. That's come off. I'm going to take that hydrogen off. I've got this sort of awkward situation. So because I've got the luxury of redrawing it, I'm going to redraw it. I'm just going to sort of slightly stick my benzene ring a little bit higher up so it's less in the way. Make that bond a little bit longer. And there we have it. We've taken off the H of my OH. And we're just going to extend it beyond the brackets. Then we've got this section of polymer chain. So all I've got to do is identify where the ester group is. So the C double bond O, and break those bonds between the C double bond O and the O. There. Once I've done that, that is a repeat unit. Let's see if we can draw the monomer. So let's draw it exactly as it is. CH3, there is an O, there is a C and a double bond O, and then all I have to do is stick those bits on. In fact, what I've drawn is lactic acid. If you're paying attention, it's exactly the same monomer that we had a moment ago. Okay, let's talk a little bit about our properties. These have gone the wrong way around. So polymers are molecules, so they have molecular structures, but they're slightly unusual because they are very large molecules. So if we look at the top one, what we've got here is polyethene. Now we should know that ethene or ethane are hydrocarbons. Small hydrocarbons are gases, but the longer they get, the stronger their intermolecular forces come. So although this has only got London forces or van der Waals, instantaneous induced dipoles between the molecules are long, so they're relatively strong, which explains why polyethene is a solid, but also it's a flexible solid used for making plastic bags, because we can quite easily pull the chains past each other because they're not actually joined to each other with covalent bonds. And also it's actually got a relatively low melting point. It's quite easy to melt a plastic bag. And then of course we could have functional groups in between the polymer chains. So this polymer chain would have hydrogen bonding, and we'd expect it when comparing a similar mass, a similar MR of molecule, to have a higher melting point than polyethene. Well, it's got to be the same mass, otherwise it's not a fair comparison because of this increase in London forces when we increase molecular mass. So you can have hydrogen bonding, and in fact this polymer, I believe, is actually one that will even dissolve in water. So things like those plastic laundry bags or those little things around dishwasher tablets that disappear, it's because they're dissolving in water. And then we've got this one at the bottom, and the reason I put this in here is because of the benzene rings. So if you were to take my polyethene, if it's a regular chain actually, the molecules have a very large surface area and they can pack together really, really well and get a lot of strong London forces between them. But if we look at this molecule here, having a benzene ring gets in the way of those intermolecular forces, those London forces. So it doesn't improve the surface area because actually these benzene rings are not going to be nicely organised like that. There'll be some sticking up and some sticking down, which means that the polymer chains can't actually get as close. Doesn't have to be a benzene ring, it could just be methyl groups or ethyl groups, any kind of bulky group that is not polar, so it's not going to add some more intermolecular forces, is going to get in the way and actually probably lower the melting point. And if you've heard of molecules called plasticizers, which those are the things that sort of like you can smell when you get a new car smell or new plastic. And you can smell plastic, which is weird. You shouldn't be able to smell plastic. It's actually molecules containing big benzene rings, so aromatic compounds, that are stuck in between the polymer molecules, pushing the chains apart. That makes them softer, hence the word plasticizer. Other properties, so those are the physical properties. The thing about chemical properties of addition polymers is they are very inert, as we know or should know if we think about plastics and the environment. So, and the reason they are is because they are non-polar. They've got strong saturated carbon-carbon bonds. So they've got nothing in the molecule that we know causes a sort of organic mechanism to happen. They don't undergo addition reactions, they've got no double bonds, they don't undergo substitution or nucleophilic reactions because they have no dipoles. And even if they have a polar group in the side chain, that isn't going to help breaking up the whole long molecule. And so that is why addition polymers are very chemically inert, which is a benefit. If I want to wrap my food in an addition polymer, I don't want it to react with my food. But that's also a disadvantage because they will persist in the environment for thousands of years. They can't be broken down by microbes because there is no bond like this in nature. So all natural polymers are condensation polymers, which means that enzymes don't really break down carbon-carbon bonds. Compare that with condensation polymers. Let's think about our melting points. Well, polyesters have got permanent dipoles between their chains, but no hydrogen bondings. So they might have a little higher boiling point than a polyalkene of a similar molecular mass. And even stronger, if you have a polyamide, which we haven't done too much about, but has a C double bond O attached to an NH group, which is also a condensation polymer, they have hydrogen bonds between their molecules. We said that all natural polymers are condensation polymers, so DNA, for example, a lot of proteins are polyamides, and proteins are held together, their primary structure, by hydrogen bonding in between the chains. And I've also included this diagram, which is of Kevlar. So this benzene ring with alternating carboxylic acid and amine groups is the structure of Kevlar, which is used to make bulletproof vests. So it's obviously a pretty strong polymer. And the reason for that is because the benzene rings in Kevlar are not on the side of the chain, they are part of the chain. So if you follow it along, actually the polymer chain is made up of benzene rings. Benzene rings are perfectly flat, they have a huge surface area, and they are holding the NH and the CO bonds in the perfect position so that they can form exactly the maximum number of hydrogen bonds with the corresponding groups in the other molecules. At the same time, you've got really strong London forces because these guys are able to pack right on top of each other with their benzene rings. So you're maximizing all the intermolecular forces, which is why Kevlar is really, really strong. So if you put benzene rings in a chain, you have a much higher melting point. If you stick them off the edge, so they interrupt forces between molecules, it's a low melting point. And then finally, let's talk about the reactivity of condensation polymers. So condensation polymers, of course, are more reactive. And if you've done about esters and amides, they can do what's called hydrolysis reactions, which is the opposite of condensation. And as we've already mentioned, the ester group and the amide group are common in nature. So amide is present in peptides and proteins. The ester group is present in polysaccharides such as starch, glycogen, cellulose, etc. And so they are already present, which means there are enzymes that can catalyze the breakdown, the hydrolysis of these polymers. They'll also break down, so they are biodegradable, meaning they will be broken down by microbes. And they can also be broken down by acids, alkalis, heat, much more easily than could your addition of polymers. Again, advantages and disadvantages. So the advantage, of course, is that we can make biodegradable polymers, so if they're single use, they will break down over time. The disadvantage is that those breakdown tends to need quite specific conditions. They don't always break down. Also, it's a bit of a waste of raw materials. If something is going to break down, it's not going to last as long. It's not going to be as chemically inert, and so we can't necessarily use it for all of our purposes, because we might not be able to put hot food in it, for example, because it might react with the acids in the food. And that's about it.